Hi everyone, my name is Infdev and welcome to the Functions and Foundations lecture series. This series is not like another programming language guide. It is focused less on memorizing syntax and more on understanding the why and how things work, which means we'll dig into the mathematical foundations of computation, hence the title Foundations. In the series, we'll be looking at functions, logic, proofs, and how these ideas show up in programming. So before getting into all the technical things, allow me to explain why I have created this series. So I'm a third-year CS student, and I have been programming for a while. I tend to know a little bit about programming everywhere, whether it's games like Unity and C#, or web, which is mainly JavaScript, or native, which is mainly C. However, one thing that has really caught my attention is functional programming, or FP for short. For me, it really connected what has been the mystery for me, which is math and CS. So, as you might have heard, a lot of people said that in order to be good at CS, you need to have a strong math foundation. And I didn't really get it back then, because why does solving for x or using the quadratic formula have to do with programming? Well, functional programming is what bridged that gap for me, and hopefully you can see too at the end of this series. So, additionally, I was also frustrated at why newcomers to programming, especially in universities, are required to learn an object-oriented programming language first, or OOP, like Java, instead of learning actual computation, which is closely related to the discrete mathematics course that they're usually required to take. They are forced to learn the language quirks, syntax, and bad code that are so common to the point that they are called patterns. So that is why I created this series. Instead of simply another programming language course, we are learning the foundations and see how they appear in programming over and over and over again. Because programming isn't just giving directions to a computer, it is creative thinking and how you can solve problems using the tools that you are given. So for this course, we'll be using Scala 3. And the reason that I chose Scala 3 is because that it has a nice middle ground between both theoretical and practical programming. And it borrows a lot of ideas from functional programming concepts while being practical enough to build real enterprise-grade software. It also has an indentation-based syntax, which, in my opinion, forces you to write clean code. However, you can still use brackets if you like. So, what exactly is functional programming? It is a broad programming paradigm, but at its core, there's four main ideas. First, pure functions. A pure function takes an input and produces an output without changing anything around it. A function f of x equals x plus 1 always returns the same value when you pass in the same x. It doesn't matter the weather or the day of the year is different. When you pass in 1, it will always give back 2. In functional programming, pure functions makes programs easier to reason about because the same input always gives the same output. I use the word side effect here, but it basically means that it does not do anything else other than to compute the result. The second idea is immutability. Instead of modifying existing data, we create new versions of the data. It might sound like a small difference, but it changes the way we design programs. Think of it like solving an equation. When you solve for x, the x is always going to be the same, and it doesn't change when you move other parts of the equation around. In functional programming, when you assign some value to a name, it shall not be changed for the rest of this program, well, usually. The third idea is first-class functions. In the world of functional programming, functions are treated as first-class values, which means we can store them, pass them around, and compose them like any other value. Lastly, decorative programming. In functional programming, you often do not see for or while loops like you would do in other programming languages. Instead, recursion and higher-order functions, or HOF, are preferred. It eliminates the common bugs from imperative programming like one-off errors because it does not require state mutation, which basically means increasing counters in loops and modifying data. It also makes your code a lot easier to reason about due to their deep ties with mathematics. Note there are a lot more to functional programming that I did not mention, and they're all very, very interesting concepts. So feel free to look into it more. This series is mainly for people who are interested in learning functional programming, especially CS students who want to connect computer science with mathematics. However, you don't need to already know functional programming or their underlying math concepts because I will explain them to you. Basic programming language helps, but if you don't, it's okay. I'll try to explain everything, and you're free to leave a comment for me to clarify anything you don't understand. Additionally, if you have never encountered proofs and logic before, it might be a little bit confusing and it does not feel like traditional math to you. I'll try to be slow and explain every step when there is a proof. And if I miss anything, please point it out. Okay, so this might be the controversial part of the slides. Why functional programming language instead of object-oriented programming? By the way, the goal isn't to say that OOP or object-oriented programming language is bad. It is very widely used and it is that way for a reason. I don't have any hate for it. I just want to point out some of the flaws. The difference between functional programming and object-oriented is that it just encourages a different way of thinking. Also, by the way, if you're confused about some of the terminologies I use, don't worry, I'll explain them later in the other lectures. However, if you are really interested, you can scan the QR code at the top right, and it contains a list of words that I might use throughout this part. So one of the common things with object-oriented programming is that state in objects can change internally. When calling a method, it changes state somewhere else in the program. It can become very hard to predict what happens. It requires the programmer to mentally keep track of more things at the same time, which makes the code base harder to maintain. While functional programming tries to avoid this by using immutability and pure functions. Instead of changing something, we transform it into something new. Global and shared states are strongly discouraged because it makes the code more difficult to reason about. Another motivation is reducing unnecessary complexity. So in some object-oriented programming languages, most notably Java, new learners spend more time dealing with inheritance, overall structure, naming, and writing duplicated code over and over again, which they're called boilerplates, while ignoring or giving less focus on the actual computation parts. While functional programming eliminates a lot of the structure boilerplates that object-oriented programming languages have. Instead, it focuses more on the transformation between different data. The next one is more specifically a Java issue. So in Java, if we have two identical objects, they are not equal. If you use the double equals naively, this is because Java compares the memory address instead of the actual value, which is often what we do not care about. And this is not the case in functional programming. With algebraic data types, or ADTs, two users with the same information can be considered equal, even though they are separate objects. Lastly, in object-oriented programming languages, inheritance is a form of abstraction, is considered a form of abstraction by a lot of people. For example, a class cat is a child of class animal. Well, this is a pretty simple example, and it doesn't look like much issue. This becomes problematic when relationships get complex, and hacky methods were invented to fix this problem, like mixins. So if you do Minecraft modding, you would know what mixins is, and it helps a lot. And in functional programming languages, it often prefers composition over inheritance. With algebraic data types, we can represent relations with sum and product types without the mental image of inheritance. So these are some of the resources I'll be referencing a lot. One focuses more on Scala and functional programming, while the other focus on mathematical foundations behind those ideas. If applicable, we'll also put the corresponding sections of the material in the slides. They're both free, and you can scan the QR code to access them. Lastly, this is the table of contents for the series. We'll start with the foundations, which are logic proofs, and the idea that computation itself is mathematical. Then we'll move on to functions, recursion, and data modeling, and connect these mathematical ideas to programming. And after that, we'll explore deeper on functional programming concepts like abstractions, type classes, effects, and finally, how functional programming works in real-world applications. Thank you for listening. I hope this series will give you a different perspective on programming, not just as writing code, but as a way of expressing ideas more elegantly.